The next part of the guide is involving natural logs. So you are used to log base 10. Okay, so when we did all our log laws, we always used log, and that means it's base 10. So that's the log that's on your calculator. And that was pretty easy to use. There is also natural logs. So natural logs have a different base. So instead of base 10, they are base E. And E represents Euler's number. And it's a constant. It's kind of like pi. It's a number that is approximately 2.71828. It's like pi, it goes on and on. But generally, it's about 2.71828. And natural logs are used more in nature and business models. And they go by a different name. So instead of using log, we use the abbreviation ln. So pronounced ln. And it is the Latin name for Logarithmus naturali. So that's where the L and the N come from. So we use the ln instead of log. So ln is base E. So if you looked up on your calculator, you will also see the letter E in there. So you might see e to the power x on your calculator, which is in exponential form. So again, you can switch back and forth, just like we did with logs. You can switch back and forth between exponential and log form. We can switch back and forth between e to the x and ln e to the x. So all the log laws that we did with in the last unit, so product rule, power rule, quotient rule, change the base formula, we can use with natural logs. Equals, so E is about 2.718. So for example, we are solving for x. So e to the x equals 5 cannot be changed to the same base. E is a number, right? We just said what e, and that's obviously not a multiple that we can change 5 to. So we're going to, instead of logging both sides, we're going to ln both sides. And then we'll bring down the x. So this is like our power rule, except we're using ln instead of log. So x will be ln of 5 divided by ln of e. Well, ln of e equals 1 because ln has base e, and e to the power 1 equals e. So ln of e equals 1. And so ln of 5 divided by 1 is just ln of 5. And if you wanted a decimal value, you could just type that into the calculator. You should have a ln button, which is nearby your log button, and it's approximately 1.61. In the second question, we can do the same thing. I'm just going to move this out of the way here. Don't really need that. So we'll ln both sides. So e to the power 2x equals ln of 12. So 2x will be ln of 12 divided by ln of e, which we know is 1. So ln 12 divided by 1 is ln 12. And then x will be ln 12 divided by 2, and then we can just change that to a decimal, so it's 1.242. Likewise here, I'll ln both sides because I can't change the same base. We'll bring down the exponents and we'll divide ln 28 by ln e, which is just 1. So x minus 2 equals ln 28, and then we'll just add 2 to isolate for x. So ln 28 plus 2, and you can just type that into the calculator. Sometimes it's given in ln form, and it's easier to change it back to exponential form. So ln x means ln base e of x because there's no number given there. So e to the power 2 equals x. So this time I'm changing back to exponential form, and then I'll just type in e to the power 2 in my calculator, and I get approximately 7.39. And then finally here, same thing, I'm going to put it in exponential form. So e to the power 4 equals x minus 1 squared. Well, e to the power 4 is just a number. So I'll type that into the calculator, and it's approximately equal to 54.6. We want to get rid of the square, so we'll square root both sides. I'll just do that here. So that works out to be 7.523, and then we'll just add 1. Okay, so sometimes it's easier to put it back into exponential, so you can change back and forth according to the question and what type of question it is. Okay, here's an application. So we have a model given, an exponential model, where we have 5,000 insects initially. So this is my initial value. The base is e, and then to the power 0.02 t, where t is the number of days. So the first question is, what is the initial population? So we're just finding the population at 0. So we'll just substitute in 0 in for t. So any base to the power 0, of course, is going to equal 1. So the initial population is 5,000. And we could tell that just by the function given, that we always have starting value times the base. So we already knew that 5,000 was the starting value, but you can just put in 0 just to clarify that and confirm that. Okay, B says how many insects will it be after a week? So we want 7 days. So we want population after 7 days. So we'll put in E 0.02 times 7. And then that's just a matter of typing that into the calculator to get the result. Okay, so it's just a matter of putting it in. And then C says how many days will it take to reach 15,000 insects? So in this question, we want the final value, or the final population, at 15,000, and we will be solving for t. So the first thing I'd want to do is isolate for the base. So we will divide by 5,000 to get rid of it there, and we'll put it over here. That gives us 3. And then we will ln both sides. And then let's isolate for the variables. So we'll bring down the power 0.02t, and then divide by ln e. So that's going to go over here. Well, we know ln e is 1, so that's just going to be ln 3. And then we can just divide by ln 3 divided by 0.02 will give us the value for t. So t works out to be 54.9 days approximately. So it's very similar to solving an exponential equation, except you just have a different base. So you have base e, or you use ln. But we solve these exactly the same as we would with exponential functions.